I'm presenting well, the process regarding the process used for additive manufacturing, the laser metal deposition. But first of all, I will give a general overview of additive manufacturing processes. And as some of the presenters have shown, and here you can see also here all the current additive manufacturing technologies, ranging from photopolymerization, material extrusion, material jetting, binder jetting, powder bed fusion, jet energy deposition, and sheet lamination. For any of these technologies, you can see several sub-technologies. For example, for jet energy deposition, you have laser jet energy deposition by laser or by arc welding or electron beam melting. Going to the technologies that we are interested in is those that are relevant for for manufacturing metal parts. For example, you can see here you can produce metal parts by fusion, by powder bed fusion technologies like laser powder bed fusion or electron beam powder bed fusion. Also by jet energy deposition, but also by sintering, as like binder jetting using a binder, and then subsequent processes like eliminating this binder and then sintering of the part. In our case, in Integradde part, we are mainly focused in jet energy deposition technologies like laser or wide arc. And well, the definition of this process is that it's an additive manufacturing process in which focused thermal energy is used to fuse materials by melting, as they are being deposited on a base plate or on the previous layer. So depending on the three main technology parameters, we can divide the energy position by the energy source, the feedstock, or the feed direction. Regarding the energy source, you can use a laser, an electron beam, or electric arc. By feedstock, you can divide it in powder and wire, and by feed direction, you can also divide these technologies in coaxial, where the material and the energy is applied coaxially, or in the side feed direction, where the feedstock is fed laterally to the energy beam. As any other presenters have shown, there are a lot of different nomenclature for all these processes, depending on the feedstock and the technology we use to provide the energy beam. For example, if you use wire, you can have different energy source like electron beam, and then you will have a jet energy deposition by with wire by electron beam. You can have also with wire, you can have jet energy deposition using wire by laser, and you can have jet energy deposition using wire by arc. And regarding powder, you can have jet energy deposition using powder and applied by laser. The general nomenclature that is used is GED, used by the initial of the feedstock, wire or powder, and then the applied energy source, electron beam, laser, or wire arc. But as you can see, the most famous or common nomenclatures for DED by wire arc is one, that it means wire arc additive manufacturing, and for DED with powder and laser, we use LMD, and for wire we use LMD wire. So, but you can find a lot of different nomenclatures in the bibliography. Also, you can find different trademarks. For example, for LMD, you can find lens, that is a trademark by an American company, Optomec. And in this case, DAD has presented the following advantages. These technologies take previous knowledge from welding, for example, in laser beam welding or wire arc welding, in this case, and also from cladding technologies like laser cladding or even arc wire cladding. It has been mainly used also for machine refurbishment and utilization. It can allow material savings. For example, in aeronautics is used the concept low bite to fly ratio. That is the amount of material that initially used to the weight of the component that actually is placed on the airplane. You can also produce small batches of customized products, making by order. It can use not only for additive manufacturing, but also for in situ repair, for maintenance, and also it can be used for rapid prototyping to see whether some design is good for the final component, or it doesn't meet or do have some problems regarding manufacturing or mechanical properties of the component. So you can easily change the design and produce another part to check if everything is okay. The main overcomes are, first, that is it needs a complicated robot and CNC programming. Also, it has to be analyzed by NDT technologies to check the appearance of the defects like cracks, porosity, and so on. And in most of cases, it needs a post-processing, mainly some finish like, sorry, like for example, some machining, polishing, with blasting to get a good surface. Regarding laser metal deposition, we can, well, is as the name said itself, is based in laser as an energy source. Laser is an acronym for light amplification by stimulated emission by radiation, and it is produced. Well, is this to achieve this? Well, to get this energy, you have to get the citation of the emitter of the emitter component, so that when it can be done by, for example, for by electric discharge, or even also by light, and when the molecules or atoms of the emitter achieve this excitation, it relaxes through emitting photons of a specific wavelength. So by designing the geometry of this emitter and the optical cavity of the laser, you can stimulate the emission of the stimulated emission of the other items and molecules, and in a selected direction. So what you get is an energy beam with that is coherent. So it's easy to be focused in a small spot with a high intensity, a high energy. Is nearly monochromatic, so it's just almost one or very narrow wavelength. It's very directional, so you get a relative narrow beam in a specific direction for a long distance. And also, regarding the meter, you can classify this laser in different types, by solid or gas, or even more specific in the geometry of the manufacturing of this emitter. You can have also fiber or disc laser, or even diode laser. And this energy source is used for very different laser technologies. You can use it for laser welding, for surface treatment, also for powder bed fusion of metals, plastics, or polymers. And in our case, in the Integrate project, we are using it for NMD with wire and powder. What we use, as you already know, we are using as feedstock both powder and wire. This the component that we are fabricating by additive manufacturing consists of different layers. So the properties of the final component depends on the uniformity of these layers. That also depends on the properties of the powder we are using. This, as has been explained in the previous presentation, the properties of these metal powders are strongly influenced by the manufacturing method, that usually is atomization, and also the manufacturing process conditions during LMD. We also need sieving of these powders, because as you can see in the table on the right, for example, for DAD, we can use a fine powder size between 25 or 45 micron, but we can also use, depending on the precision we need, or the precision rate needed for the specific applications, we must even go to powder size between 45 and 100 micron that are also used, for example, in electron beam melting. And for example, as a comparison, you have here also for powder bed fusion by laser, and that the powder size are finer, between 15 and 45 micron. So as we are using just very fine particles, we have also to consider safety precautions when handling these powders during manufacturing. The other type of feedstock we are using is wire. In this case, we are using solid wires that are already used in arc welding. That they came in drums or spools, and we are using diameters ranging from 0.8 to 2.4 millimeter, depending on, well, just again, in the precision required to manufacture the component, and also the requested deposition speeds that could be needed. You see that, well, for if the diameter is higher, the deposition rate is higher, but also the energy needed is also, it has also to be increased, but it's not this ratio is not proportional. The energy needed is not proportional to the diameter. You have to take into account that the energy needed depends on the square of the diameter. So if for 0.8 you may need 500 watts, for 1 millimeter you may need for 1.6 millimeter you don't need the double. You need the double, the square of the double, that is 4 times more, not twice times. So you have to go not to 1 kilowatt, but to go to 2 kilowatts. So if you want to use, for example, 2.4 millimeter diameter, you would need maybe 5 or 6 kilowatts to deposit a good quality layer. And also the auxiliary equipment we are using, the contact tubes, the drive rollers, the wire feeders, are the same material that is used for arc welding. So we are using the same equipment. Regarding the equipment, you need a laser source and also a laser head with the required powder nozzle or wire nozzle. For example, you have here several types of lasers. You have fiber laser, 2D laser, CO2, or diode laser. Also, you can use different movement systems like robots, CNCs, also auxiliary or external axis for coordinate movement needed for the production of the manufacturing of complex parts. Also, you need shielding gas that you can provide it with the laser head here. That can be also that could be injected by the same laser head. But if the component requires a very low oxygen content, then you have to go to big chambers that should be filled with inert gas to assure the quality of the final component. Also, for the LMD powder, you will need a powder feeder. You can see here several types of them with their, for example, you can see here where the powder is filled here, and you have, depending on the sophistication of the powder feeder, you have also some powder, also powder flow control. That, for example, for high precision manufacturing, you would need a very constant powder flow that could be provided only by for very precise powder feeding system. MD-wire, as I mentioned before, we are using conventional arc welding systems where we use this wire feed, for example, this equipment for furnace to get a precise wire, a constant wire feeding. Specifically going to LMD powder, you can see here the powder is injected on the same point of where the laser beam is focused. So we are melting this powder on the surface of the base plate or on the surface of the previous layer, and we are producing a laser track or laser bead. So we have to deposit several subsequent lines to produce a layer, and upon this layer, again, overlapped tracks to produce the next layer. And the main advantages of LMD power is that, well, we can get medium to high deposition rates. Also, we can produce medium-sized parts. They are near net shape components, so we will need further surface finishing. We can use a wide range of materials, even multi-material or functional integrated materials, and we can use it also to repair or manufacture damaged components, not only to manufacture them. The limitations. Well, the limitation is the equipment cost, mainly the laser and the manipulating device, the robot or the CNC machine. Is the rather low resolution, and as I mentioned before, most of the components produced by LMD powder needs of some post-processing. In this case with the LMD powder, the main feed direction is coaxial. Here you can see two different coaxial nozzles. The first one consists of 3 powder beam that converge in the same point, and this is a coaxial nozzle where you are producing a conical powder flow. In this case, the powder distribution is very homogeneous. You have a high powder efficiency in a small spot, but you have the limitation for working in tilted position. Here, the best position is just the vertical one, or you can go maybe to 20-25 degree tilt. On the contrary, well, the 3 beam nozzle, there are also some nozzles that instead of 3 have use 4 beam nozzle. But in this case, this coaxial nozzle with several powder flows or powder beams, they can easily work in horizontal position, not only vertical or tilted. You can go to horizontal position. They are suitable for higher laser power, but in this case, the powder efficiency is worse. Unless you are able to fit the laser beam diameter so that it's a bit bigger than the powder distribution diameter size in the point that where the three beam nozzles coincide at this point. There are several commercial powder nozzles, for example, from multiple outlets, Coaxial nozzle from Fraunhofer ILT, or this Coaxial nozzle from Fraunhofer IWS. And this, well, the scenario is applied for different industrial sectors like turbo machinery, aero and automotive components, molds and tooling, subsea and offshore. The amount of materials that you can process is quite large. Different steels, even some tool steels, nickel-based alloys and cobalt-based alloys, titanium alloys, and also carbides in a metal matrix. And although you have to take into account that some of these materials will need some post-heat treatment. For example, some nickel superalloys or even some titanium alloys should undergo a post-heat treatment to achieve the required mechanical properties. Here at the right, you can see one component. It's the component of it's a part of an airplane engine produced here in Gaiman. Well, as you can see, the speed accelerated. The total weight of the component is the total weight of the component is 1.7 kilograms, and the manufacturing time was 3 hours. As you can see here, first we deposit layer by layer the first cylindrical wall with some nerves, and at the end we have to tilt the external axis to be able to grow the final part that was tilted 45 degrees. So in this case, we with this external axis and coordinating the movement with the robot and the two external axes that has tilt movement and also rotation movement, you can avoid hanging, or you can manufacture hanging structures just in vertical position, just by changing the orientation between the robot and the external axis to be able to produce this kind of part. That is one of the, as you can also see in the previous presentation, is one of the main advantages of LMD and DAD processes. With MDI, as you can see here, the wire is fitted in the same point that the laser beam is inciding on the base metal, on the base plate, or the previous layer. In this case, you can see that we have a lateral feeding of the wire, and the main advantages is that we get a high deposition rate. We can produce medium to large size parts. We get also near net safe components with a wide range of materials, and also we can be used to repair manufacturing. And you can utilize equipment for laser welding, or for example for DED by arc welding. Limitations. Here the resolution is even lower than with powder, and we need most of the time is post-processing, and it's a very rigid process, mainly due to this lateral feeding. You can see here that depending on the direction, if the laser is leading or the laser is trailing, the results are different. For example, for laser leading, we have more dilution because we need also higher power. And for laser trailing, we need lower power, and the dilution is good, but it's not so high as when the laser is leading. To solve this, there are several systems, 2 or 3 systems that can feed this wire coaxially to the laser. For example, this system from Precitech that is being used in Integradde by one of the research centers, IDEPA in France. In this case, well, what they use is a beam shaping to produce a ring, or to produce a laser beam that actually is a ring around the wire. As you can see, the wire is fitted vertically, and the laser ring is produced on the same point over the base plate to melt the wire. For example, here it's a quite simple geometry. As you can see, comparing with the lateral feeding, you can move in any direction and you have the same result independently of the direction of the movement. You can see how it produced the cylindrical part. After several minutes. For example, this other part with several changes of direction, as you can see, well, and this could be now possible with lateral feeding, because the results will be different in any point of the component. And you can see here the different parts that were produced by IDEPA. You can see as a comparison on a smartphone there. Regarding the process strategy, you can see here the workflow that was already mentioned in the previous presentations. You have a previous optimization by design using simulations or modeling. Based on that, you can get the final design of the part, and then translate it to the machine language, and to produce the part in a robot or in a CNC machine. And after, in order to manufacture the part, you have to prepare the material, the machining, and proceed to the manufacturing. As I mentioned before, you need a post-processing stage where you first you need to scan the component to analyze the geometry. Also, maybe some post-processing, heat treatment, machining, polishing, and at the end, the final inspection by non-destructive testing. In order to optimize the strategy, the process strategy, you must consider the different parameters or processing parameters as input: the beam power, the deposition speed, the spot size, preheating, overlapping between tracks to produce one layer, the strategy deposition of the different layers and the different tracks, the material composition and the feed rate, also the substrate composition and the optical properties of both materials, and also the silting gas type and flow. So first, we produce single tracks to check the track integrity, uniformity, and also the dimensions, the width and the height. Based on that, we can go to the production of layers by studying the layer integrity, layer height, or if we are producing thin walls made by a single layer, you also check integrity, uniformity, and the geometrical and dimensional accuracy. So then, using this information from this processing or these tests regarding the single tracks and the layers or thin walls, we can produce or manufacture the 3D part and check in this 3D part the integrity, the dimensional accuracy, and the geometrical accuracy, the distortions, visual stresses, the metric structure, the mechanical properties, and also the surface roughness. And depending on that, evaluate which surface finishing operations must be going on, or if it needs a heat treatment. Following the Integradde project philosophy, in considering additive manufacturing as a digital manufacturing, you can see here that we are to produce this component. It's also a part of an airplane engine. First, we are designing this component. We are simulating the manufacturing by LMD powder of this component, checking mainly the distortion. You can see here that this place the distortions, or there is an accumulation of distortions there. You must to take into account to maybe redesign the component to produce the final component by LMD powder in this case. Also, at the same time that we are manufacturing, we are looking at the thermal print in each point of the manufacturing process of this component. So we are registering the thermal image of the melt pool, but also for each robot position. And also we are registering the speed, the processing speed in each time, and we can, with this data, we can produce this 3D visualization of, for example, in this case, heat accumulation in the component. You can see that there's some parts that where the accumulation of heat is higher than others. And finally, we can analyze the component regarding the geometry. This is a three-dimensional laser scanning of the component, and you can see here the deviations regarding the initial design of this component. You can see here that the inner part, the deviations are lower than the external part. And for example, these are here in this part of this region of the component, there is a large deviation. I think it was about 1 millimeter. So the idea is with this additive manufacturing is use less raw material and reduce time to market and also the cost of the component using data analytics and artificial intelligence. We are using for that a protocol, the automation ML protocol, where we produce a master file where we store the design file that through topology optimization, we get the optimized design file that also is part of this master file, but process simulation, we get the simulation file, and by slicing and path planning, we produce the build file, and during manufacturing, we get the information from different sensors to get the process file, and afterwards, after the NDT and data analytics, we get the final variation time. Sorry, the final variation file, and all these files are part of the automation ML master file. Okay, that's all for my part, and well, I think the questions are up to the end of the day.
Yeah, exactly. Thank you, George,